In this presentation, we'll be discussing electromagnetism, which is the relationship between electricity and magnets. Magnets, although they seem simple to us from the outside, can be very complex on the inside, and we'll be taking a look at what makes a magnet a magnet. Electromagnetism, or the electromagnetic force, is one of the four fundamental forces. It generates light and energy and holds atoms, matter, and the world as we know it together. The narrator of one of the source videos from the National Geographic opened up with that profound line that I did not fully appreciate until the end of my research for this project. Electromagnetism is a branch of physics that studies the interaction between electric and magnetic fields. But to gain a better understanding of electromagnetism, we can begin our journey by speaking about the electron and its fundamental properties. Electrons are negatively charged particles that have a quantum property called spin. And what that means is that it's spinning on itself. The particle itself is spinning or rotating on itself, and it generates an electric field that radiates outward in all directions, a static, outward, three-dimensional in every direction. When that electron is in motion, the disturbance from that field that's going outward creates an elliptical magnetic field around the particle. And this is what allows these particles to behave like little magnets. In this slide, we can see how that works. Because the way the particles are aligned in an element or a material can form a magnetic field. So if you can look at the top where it says ferromagnetic, all of the poles are aligned with each other. So all the north poles are facing north, all the south poles are facing south. So that would be like iron. Iron is ferromagnetic, so all the particles in iron are going to be aligned just like that. And on the bottom it says anti-ferromagnetic, and that is when the poles are canceling each other out. So all of the particles in that element are canceling each other out. So whatever element that is not going to emit a magnetic field or a strong magnet or any at all, as it's canceled out. In this slide, we have Maxwell's equations, which is the math behind the four fundamental principles of an electromagnetic field. The first one is Gauss's law, explains that an electric charge acts as a source for the electric field. So that would be a charged particle of some sort. The second one is standalone magnetic charges cannot exist. So that means a monopole doesn't exist in nature. A magnetic north pole always comes with a south pole. So if you cut a magnet in two, you end up with two magnets with dipoles, each with their own dipoles. The third one is a disturbance, Faraday's law, which is a disturbance in the magnetic field affects the electric field. So this explains induction, which is a change in the magnetic field can induce an electric current running through a wire. So a real world example of this would be like wind turbines, nuclear energy, telephones. The fourth is an electric current or change in the electric field leads to a disturbance of the magnetic field. And this disturbance of the magnetic field in turn disturbs the electric field. And this alternation between the two is what creates electromagnetic energy. And that comes in the form of waves. So that's what we see, or what everything is an electromagnetic wave, which was pretty cool to find out at the end of this. But yeah, so those electromagnetic waves are microwaves, X-rays, infrared, visible light, gamma rays. The whole electromagnetic spectrum is what that is. And yeah, that's what I found really interesting about this, was reading these laws, or these principles, sorry. I found it fascinating to learn that electromagnetic waves are present everywhere. Everything is made up of electricity and magnets. Um, and the electric and magnetic field are definitely inseparable, and one is the origin of the other.